Applied Physics Video Slideshow over Fiber Optics by Kunahl, Chopra, and Austin Nutt. In this video, we will be covering the basics of the technology of fiber optics and the physics behind it.
Fiber optics is a method of communication by relaying electromagnetic waves traveling at the speed of light along a medium of glass or plastic. Light is bounced along the inside of a reflective tube and received and decoded by a light-sensing photoelectric cell. Fiber optics is being implemented into our internet connection and our cable connections. Fiber optics is being used more and more over copper wiring as time goes on, and soon fiber optics will be the main source of our internet and cable connection.
The modern fiber optic cable was first experimented with and implemented in the 1970s when the CIA wished to communicate between its stations without an endangerment of interference in their communications. However, the first discovery that led to its invention occurred much earlier, the late 1800s. John Tyndall first discovered that light could be bent through a stream of flowing water, and shortly after that, Alexander Graham Bell invented the photophone. This device recorded signals sent by reflecting sunlight in long-distance mirrors that vibrated when the user spoke. When a mirror on the other end picked up those vibrations, it decoded them back into a voice. This was a key step in understanding that patterns of light could function similarly to the electric signals sent by the telegraph.
In order to comprehend fiber optics, one must grasp the key concepts that make up the basis of this topic. Fiber optics is built upon three main ideas: total internal reflection, index of refraction, and waveguides.
The index of refraction is the value of a certain type of material that describes how light propagates through a medium. It is commonly known as N. It is described through the equation N is equal to C over V, where C is the speed of light and V is the phase velocity of light through that medium. For example, the index of refraction of water is 1.333. This means that light travels 1.333 times faster in a vacuum than it does in water. Knowing what happens to light as it passes through a surface is critical to fiber optics. Specifically, what happens when the refractive index of the outside of a cable is less than the refractive index of the inside. More on that later. The material used in fiber cables is plastic, or occasionally even drawn glass or silica. The refractive index of plastic is 1.460, which means it travels 1.460 times faster in a vacuum than it does in plastic.
Total internal reflection is the reason why fiber optics is incredibly efficient. Total internal reflection occurs when light strikes a medium with a certain index of refraction at a certain angle. If the angle is correct and the internal index of refraction is greater than the index of refraction of the outside of the medium, the light reflects back internally in the fiber cable and rebounds off the walls all the way across the cable's length until it reaches its destination.
Here is a graph of total internal reflection when light is shined underneath water. When the angle is too small, the light is merely refracted out into the air. Once the light is at a critical angle, it will travel along the surface of the medium, and if the angle is any greater, total internal reflection can be achieved. This is exactly how light travels along a fiber optic cable, by bouncing off either end until it reaches the final point.
Waveguides are the means by which light is transmitted in a fiber optic cable. A waveguide is a kind of highway for transmissions of electromagnetic waves, like a medium for a sound wave. They restrict the propagation of waves and focus the wave's energy in one or two dimensions. This makes the information they transfer much faster and travel for longer time without needing amplification. Depending on the material, the waveguide, a fiber optic cable in this case, is made up of, the light within will behave in different ways, In order for the cable to work at all, the refractive indices of a waveguide must be very carefully manipulated.
Single-mode fibers are fibers of a certain thickness that only allow one mode of light to pass through and propagate down its length. The light does not reflect often, and as such passes through faster and goes further without needing amplification. This kind of fiber is used in cable companies for long distances. Multimode fibers, however, are wide enough that multiple beams of light can be sent down one cable, all reflecting at different angles. This unfortunately makes the signal these fiber cables send slower because the light bounces more. Multimode fibers are best used for shorter distances, whereas single-mode fibers are better suited for longer ones.
Due to the speed of fiber optic cables as opposed to copper cables, technological advancements in communication and information are increasingly using fiber optic cables. They allow for faster and more powerful transmission of data, and some cables can send 10 times the information that traditional cables can. Google Fiber, for instance, is a fiber optics network that has connection speeds up to 100 times the speed of a normal high-speed internet.
You might be asking yourself, why should we go through the hassle of replacing all the copper-based wires with optical fiber communication? Well, there are many added benefits of using fiber optic cables over copper-based wires. Fiber optic cables provide a greater bandwidth than copper wires. More bandwidth means fiber can carry more information with greater fidelity and speed than copper wire. Also, since the fiber optic signal is composed of light, little to no signal loss occurs during transmission. Therefore, data can be transmitted at higher speeds and greater distances. Furthermore, your data is much more secure with fiber optics than it is with copper wiring. Hypothetically, if the cable was tapped, it would be extremely easy to notice since the light would seep out, causing the entire system to fail. Fiber networks also enable you to put all your electronics and hardware in one central location instead of having wiring closets with equipment throughout the building. Copper wire, however, is extremely easy to tap into without any noticeable differences and is unable to be detected. Also, since copper is made of metal, it is oftentimes stolen due to the global boom of copper prices in the 2000s. No such problems would occur with fiber optics unless somebody would want to steal plastic.
Fiber optics are not yet perfect, however, and there are a small number of flaws that hold the technology back for now. For instance, fiber cables are more brittle and delicate than copper and are not as easily replaceable. If a break in a major line occurs, it can be difficult to splice the fibers back together, causing even more turbulence and problems. Fiber cables are also more susceptible to wildlife because of their fragility. Certain insects can even eat the cables. In addition, although fiber optic cables are cheaper in the long run, the initial cost is hefty and may be insurmountable for small locales.
Fiber optics are faster than conventional wiring systems. Computers are becoming faster and faster, and so need fiber optic cables to handle their strength. It will not be long before all traditional wiring systems are completely obsolete in the face of the efficiency, practicality, cost-effectiveness, and power that fiber optic cables provide.